Welcome everyone, my name is Levente Lippenszky and I will present our work on unsupervised artifact detection and quantification via contrastive learning with noise reference. Let's start with the motivation. So artifacts can make the scan unsuitable for diagnostic applications, research or integration into downstream algorithms. Deep neural networks are also known to be sensitive to image quality, so an automatic artifact detection system could improve clinical workflow efficiency and remove corrupted images from large datasets, such that we can train more robust neural networks. In our study, we leverage contrastive learning, where the goal is to learn discriminative features from query positive and negative examples. In our study, the positive is selected to have the same artifact level as the query. The query and the positive are just two random patches from the same scan. Negatives are chosen to have different artifact levels than the query. So artifact negative is basically a random patch from artifact corrupted version of the same scan, and other image negative is a random patch from a completely different MR scan. As we use patches from real MR scans as negative examples, the encoder can capture various kinds of artifacts beyond the ones that are simulated during training. This figure shows the training of the artifact encoder, where we have two scenarios, each sampled with equal probability. Let's start with scenario A, where we have the query positive, artifact negative, other image negative, and noise in the mini-match. Each patch is encoded by the artifact encoder into two-dimensional embedding space, and the contrastive loss is designed in a way that the query is attracted to positive and repelled from negatives. Also, the noise is attracted to artifact negative and repelled from query and positive. In scenario B, the query and positive are patches from low artifact version of randomly selected scan, and high artifact negative is from a heavily corrupted version of the same scan. So in scenario A, artifact corrupted patches are positioned closer to noise than artifact-free ones, which enables us to do artifact detection. In B, patches with high artifact levels are embedded closer to noise than patches with low artifact levels, which enables us to perform artifact quantification. As you can see in this figure, L2 normalized embeddings lie on the unit circle. And since we use cosine similarity in the loss function, the embedding space is structured through angular relationships. And the loss function structures the embedding space such that the query is closer to positive than negatives, and noise is closer to artifact corrupted negative than to query and positive. In inference, the artifact score is defined as the cosine similarity between noise and test image embeddings. The higher score indicates higher artifact level. This table presents the artifact detection performance of our method compared to 3 other methods across 4 different test sets. MRART is a real-world dataset containing more than 400 T1 brain scans. 3 radiologists assigned each scan a 3-point motion artifact severity score. Real Multi is a private dataset of 177 real prostate T2 scans annotated for MR artifacts. The other 2 datasets are synthetic datasets. Each row in the table reports the binary classification performance for distinguishing between the artifact-free class assigned label 0 from the corresponding artifact class assigned label 1. The best performance is highlighted in bold, and as you can see, our method achieves the best performance across the 4 test sets. We evaluated the methods for artifact quantification as well by computing the Spearman correlation between ground truth labels and artifact scores. And as you can see, the table demonstrates that our method significantly outperforms other approaches on both datasets. Regarding the conclusion and future work, we proposed a contrastive learning method that structures the embedding space such that images with higher artifact levels lie closer to a noise reference. This enables unsupervised detection and quantification of various MR artifacts in both prostate T2 and brain T1 images. Our method outperformed existing unsupervised approaches in artifact detection and quantification. And as the method does not rely on manual annotations, future work could explore the training of foundation models on a diverse range of unannotated MR datasets. Thank you for your watching, and see you at the Unsure poster session.